Hello, welcome to day 2 of integration by parts. I would like you to try the first 4 example warm-ups. Hit pause, see what you can do. I want to see if you can figure out how you might find the antiderivative. What techniques can you use? Maybe you need more than one, but start by hitting pause and trying those antiderivatives. All right, hopefully you're back and have had a chance to try these antiderivatives just to see what you think. So let's go through this first one. What would you choose? Hopefully you chose u substitution. This is a u substitution problem, and if I let u equal x squared, then du equals 2x dx, which means 1/2 of du equals x dx. So we would have 1/2 the integral of e to the u du. Integrating that, we'd get 1/2 of e to the u plus c. Substituting back in, we get 1/2 of e to the x squared plus c. All right, what about the second one? Hopefully it looks familiar. Maybe even you had your notes sheet out from yesterday, and you saw that this is an integration by parts. And if this is an integration by parts, I know there's a lot of u's that we use here, but this integration by parts, and we had it on a previous example, we would let u equal x, so the derivative would be dx, and our dv would be e to the x dx, so v would be e to the x, and then I would do u v minus the integral of v du. Oops, I said du. I meant to write what du equals, which is dx. And we can integrate that. We get x e to the x minus e to the x plus some constant. Okay, what about this third one? Hopefully you probably tried a u substitution and said, okay, well, if we let u be that chain, which would be x squared, du would be 2x dx, but I don't have a way to substitute that 2x. So this doesn't work. And maybe you then even tried integration by parts and said, okay, well, maybe I will let u equal e to the x squared. So du would be e to the x squared times 2x dx. And then dv would just be dx, and the antiderivative of that would be just x. But then you see, if we do uv, I'm going to put the v in front, uv minus the integral of v du. Did we create a problem that's simpler? Is there a way to continue to make that integral simple enough that we can eventually take it? And the answer is no, there's not. So this one actually can't be done. Not with the techniques that we have. There are computer models that could do it. We could certainly do it with a Riemann sum idea, or the computer models could, but we cannot do it by ourselves. So we don't have the techniques for that. All right, what about example 4? Probably you tried integration by parts, which means you would let u equal x, so du equals dx, and then dv would be secant squared x dx, which means the antiderivative of that would be tangent of x. And so uv minus the integral of v du. And we have a choice now. If you happen to have the brain capacity to remember the antiderivative of tangent of x, great. But if you don't, you're going to need to use a u substitution here to rewrite this integral as the integral of sine of x over cos x dx. And then we would let u equal cosine of x, so du equals negative sine of x dx. And I have a clean substitution, so we really have negative the integral of 1 over u. So we have x tangent x minus the negative integral of 1 over u du. And then when I integrate that, I'm going to get the natural log of the absolute value of u. We'll put that plus c in there. So we have x tangent x minus the natural log of the absolute value of u. Substituting back in, we get x tangent x minus the natural log, plus the natural log of the cosine of x plus c. So sometimes, just like when we took derivatives, if we had to do a chain rule, sometimes we had to do a product rule within that. Sometimes we did a quotient rule, and within the quotient rule, we had a chain rule. Same thing is true with some of our techniques for antiderivatives. Sometimes when we need to take that integral, we will have to use multiple techniques. Okay, let's go back and consider this integral that we may have looked at a couple times, this x to the n e to the x, where n is going to change. In this first one, we're going to let n be 1. So this would be the integral of x to the first e to the x dx. Okay. We already know from the warm-up, although I could use integration by parts quickly, we know that using integration by parts, we get x e to the x minus e to the x plus c. What I want to see now is how that changes as the n value goes up. So as we get x to the n e to the x dx, and we substitute n for 2 this time, so we get x squared e to the x dx, I want to do integration by parts. So I would like you to try this problem. So hit pause, try it, and then see what you get. All right, hopefully you tried this and you let u be x squared. So du would be 2x dx. And then you let dv equal e to the x dx. So v equals e to the x. And then when I take this antiderivative, we would get x squared e to the x minus the integral of 2x e to the x dx. I just put it in a slightly different order so it looked a little bit prettier. Let's clean this up again. Let's pull out my constant. What did you notice when you got right here? Hopefully you noticed something. Hopefully you noticed that when you got right here, that this looks awfully familiar. We've seen that before, right? We know that right here, we're going to need integration by parts again, right? So if we were to do integration by parts of just this one, obviously I have the answer up above, but we would let u equal x. So du would be dx, and dv would be e to the x dx, and the antiderivative there would just be e to the x. And so this problem actually looks like, we're going to come up here, x squared e to the x minus 2 times, and then I would have this new integral, uv minus the integral of v du. Well, we knew that was going to be the antiderivative of that, and we could take it one step further because we already saw this problem, or this answer right here, the result of this right here. So this would be x squared e to the x minus 2 times x e to the x minus e to the x. And I'm going to go ahead and put my plus c in here. But what happens is when I distribute that negative 2, we get x squared e to the x minus 2x e to the x plus 2 e to the x plus another constant. Negative 2 times c is still a constant. I'm going to go ahead and put it as c. Probably it would be better to write it as c sub 1, so you delineate between the two different constants, but it, for all intents and purposes, c is just fine. Okay. Maybe you have good deductive reasoning skills and you can figure out what might happen when n is 3. But I want you to hit pause and try when n equals 3, meaning I want you to take the integral of x cubed e to the x dx. Did your hypothesis come true? If we let u equal x cubed, then du would be 3x squared dx. If we let dv equal e to the x dx, then v would be e to the x. And my first iteration of this would say x cubed e to the x. So uv minus the integral of v du. I'm going to go ahead and write 3x squared e to the x dx. And we'll clean that up just a little bit. 3x cubed e to the x minus 3 times the integral of x squared e to the x dx. What does that look like? Hopefully, what you notice is that this integral right here was the integral we just had up here, which means the result of it is here. But in order to get there, we would first have to, oops, wow, that did not go well. We would first have to take the integration by parts and then do it again. And we've already done it once. So at this point, we're at 3 iterations of integration by parts. So I'm going to show you what the answer should be. We would have x cubed e to the x minus 3 times, and then this whole expression right here would be x squared e to the x minus 2x e to the x plus 2e to the x plus some constant, which again, when I multiply by that negative 3 is still going to be a constant. Probably would be better to notate it. 3x squared e to the x plus 6x e to the x minus 6e to the x plus some other constant. Maybe we call it c sub 2, although just c is fine. Okay, this could be a real pain. So there has to be a better way to organize this. It has to make more sense than this. So what I'm going to do is I'm going to show you a technique that we can do when our u function is a polynomial. So let's define a polynomial real quick. Remember, a polynomial is something that has integer, even more specific than that, positive exponents, positive whole number exponents. So if we have something along those lines, if u happens to be a polynomial, and especially when our dv is a cyclical function or something whose antiderivative just keeps going in a pattern, like it doesn't get smaller, it just keeps going back to the same thing, would be a prime time to use this technique. So here we go. Let's look at example 2 of this. Notice it is that next term. It's when n is 4. It's x to the 4th e to the x, which we know we would have to go through and use integration by parts multiple times. You are more than welcome to do integration by parts. Maybe you didn't see the polynomial and you don't think about it and you just keep doing it. Works. I'm just trying to show you a different way. So I'm going to make 2 columns. And my first column, and it doesn't really matter, this is just for organizational purposes, I'm going to put what I would let my u be. So in this case, I would let my u be x to the 4th. And then I would let my dv be e to the x dx. Okay, so I'm going to put those there. Now what I'm going to do is on this left-hand side, this column, I'm going to take the derivative until we get to 0. I'm just going to put until 0. So I'm going to take the derivative of this left-hand side until I get to 0. So the derivative of x to the 4th would be 4x cubed. The derivative of that would be 12x squared, 24x, 24, and 0. Once I get to 0, I stop. Then what I'm going to do on this right-hand side, I am going to take the antiderivatives, and I'm going to take the antiderivatives until the column matches the other side. And so our antiderivative won't get to 0, but I'm going to take antiderivatives until I get to 0. So the antiderivative of e to the x, this is a great one, by the way, is just e to the x. Antiderivative of that Keep going with antiderivatives. So each time, effectively, what I'm doing is taking this antiderivative with respect to dx. And I'm going to continue that pattern all the way down. Okay, now what I'm going to do, and this is easier to show than to actually write steps down, which is why there are no steps listed, is I am going to start with my u and I'm going to put a positive sign. And then I'm going to alternate signs. It always starts positive, and I'm going to alternate signs until the very end. Obviously, zeros don't matter. So I just want to make sure that I know my signs switch here. And then what I'm going to do is, just for visual purposes, I'm going to take these diagonals, okay? I'm ignoring the 0 because obviously if I multiply 0 by anything, it's going to be 0. And I'm going to multiply these two terms together. So I have a positive x to the fourth e to the x. My sign says negative, and then it is 4x cubed e to the x. And then my sign says positive 12x squared e to the x. And then my sign says negative, and I'm going to do 24x e to the x. And then I have a positive 24 e to the x. And once I run out of terms, then I'm going to put plus c. So this is just a quick way with when that u is a polynomial. And I could have done it in the problems before. I can even do if the polynomial is just x, although it seems silly to do that because you really only have one term. I'm going to make a table just to make my life easier. So hit pause, try example 3, and then come back. All right, example 3. You should have an answer if we start with u equals x squared and dv equals sine of 3x dx. This one's going to require a little bit more work on the antiderivative part. The derivative, thankfully, is pretty easy. And in fact, nice because it's pretty short. So it doesn't take me very long to get to 0. Now I'm going to take the antiderivative. And I know if I take the antiderivative of sine of 3x, I'm going to have either a u substitution or that undoing that chain. So this will be negative 1/3 cosine of 3x. The next one, I'm going to have a chain again, so it's going to be negative 1/9 sine of 3x. And then finally, this last one will end up being positive 1/27 cosine of 3x if I deal with that u substitution. Now when I multiply, it gets a little bit messy because my signs will change. I originally had a positive x squared, but I'm multiplying it by negative 1/3 cosine 3x. And then I had a negative 2x, but I'm multiplying that by negative 1/9 sine of 3x. And yes, I probably wouldn't show this step. I just want you to see it. Plus 2 times positive, in this case, 1/27 cosine of 3x. Cleaning this all up, we'd end up with negative 1/3 x squared cosine of 3x. That would be positive 2/9 x sine of 3x plus 2/27 cosine of 3x. And what I can't lose is my plus c. So that's just a technique to be able to take the antiderivative. Obviously, we needed integration by parts. A u sub wasn't going to work here. The u happened to be a polynomial for this integration by parts, so this table worked nicely. All right, let's look at one more tricky one. And truthfully, we won't see this come up very often. Probably not on the AP exam, but definitely in some of the upper level calculuses as we go through and do antiderivatives. Okay, I want you to think about why this maybe creates what I'm going to use quotes because it's not really an infinite loop, but why am I saying that this is called an infinite loop? Well, think about e to the x. Derivatives or antiderivatives. do we ever narrow it down? Does it ever get to be smaller, a smaller function, a different function, something that then ultimately becomes 0? No. E to the x is always e to the x, whether I'm taking derivative, antiderivative, whatever. What about sine of x? Or sorry, this is cosine of x. No, because the antiderivative or derivative of that continues to be trig functions, no matter how many iterations I take of that derivative or antiderivative. So I want you to watch. I am going to let u equal e to the x, du then will be e to the x dx. And we could go either way. I will tell you this way in this example happens to be a little bit easier. It's not easy, easier. So dv I would let be cosine of x, and then v would be sine of x. Okay, so uv minus the integral of du. Okay, well, what do we see here? We see that right here, I need to use integration by parts again. So I'm going to use it on just this portion. I'm going to let u equal e to the x. You see it kind of looks like a lost cause. So dv would be sine of x dx. The antiderivative of sine of x would be negative cos x. So uv, so I already had the e to the x sine of x minus, and now I'm going to do this integration by parts. So uv, so I'd have a negative e to the x cos x, uv minus the integral of v, I have a negative integral du, so I've got negative e to the x cos x dx. Let's clean this up just a bit. So I have e to the x sine of x minus, are you okay if I do plus e to the x cos x? This would be minus the integral of e to the x cos x dx. Are you good with that? Do you see I combined those to make them positive, but then when I distributed my negative, it made it negative again? Okay, what do you notice? Hopefully what you notice is right here, we're back to the original problem. Okay, so what would we know happens? Well, we would start here and we'd do this and we'd be back here and we'd just keep going. So this could go on forever. All right, so let's define what we already know. We were taking the antiderivative of e to the x cos x. So we said that e to the x cos x dx, so far what we know is it's equal to e to the x sine x plus e to the x cos x minus the integral of e to the x cos x dx. Okay, well, let's use some algebra. What if I combine, for lack of a better words, what if I combine like terms? I mean, technically, these are like terms. If I add that integral to the other side, I would have 2 times the integral of e to the x cos x dx, and it equals this e to the x sine x plus e to the x cos x. Okay, well, I don't want to know what 2 times the integral of e to the x cos x is. I just want to know what one of those integrals is. So the integral of e to the x cos x, when I divide it by 2, just gives me this expression that says e to the x sine x plus e to the x cos x divided by 2 is equal to the integral. And now I'm going to stick a constant of integration because I haven't put that in there yet. So sometimes when we have this infinite loop, something where we know the 2 functions, it doesn't matter if I switch the order. If I put this e to the x as dv and this cosine of x as u, I'm still going to create an infinite loop. I'm still going to get to the point where eventually on one side of my equation, I have the same thing that I had, or that I was actually taking the antiderivative of. So I'm going to move it over, and then I'm going to divide by 2. So just a technique to be able to do that, to take that antiderivative. Do these come up a lot? They really don't. It's just something interesting to look at, and the algebra behind it. So that is all for integration by parts. You should be able to do the majority of that worksheet. There's a couple tricky ones. I put asterisks by them because they're kind of fun to look at. They're not a typical integration by parts, but a unique one. Don't feel obligated to know that technique. It is not something I will test you on. It's not something AP will test you on. I just think it's interesting. So good luck on that worksheet, and we'll talk soon.